Hello everyone and welcome back to another video here at the School of Quantum. Today we are looking at NVIDIA's role in the quantum technology space. NVIDIA for sure is not a hidden champion, but the activities in the quantum space might not be known that well, and that's why they are part today of the series. So if you want to know what NVIDIA is doing to transform the quantum ecosystem, stay tuned for today's video. But before we get into it, a quick note. So if you have not seen any video of this series previously, make sure to check out our Hidden Champions playlist. And if you like to learn more about companies in the space of quantum technology, so sensing, communication, and computing, then make sure to subscribe to this channel. And with that, let's hop right into the website of NVIDIA. So here we are in the quantum computing part of NVIDIA's products and offerings, and it says NVIDIA Accelerated Quantum Center, NVAQC, providing a state-of-the-art facility for turning qubits into useful quantum computers. So this is already telling us something here. So qubits into useful quantum computers. So the idea is to come from, let's say, single qubits and probably use NVIDIA acceleration, so GPU acceleration, to turn those qubits into computers, so run algorithms, maybe also do error mitigation and so on, but we will learn about that next. What is interesting here in this image, you see in the center you have the GPU racks, I would say, the NVIDIA systems. And around here you see these symbols for the quantum computers. And what is interesting is we see different types here. So this is like a symbol for photonic computer, I would guess. This one is a superconducting one. Here we see an atom, that might be ions here. So the idea is that what they deliver in terms of technology is not necessarily bound to one specific platform, but can generalize across multiple different platforms, as for example these four here. So, what is NVAQC? The NVIDIA Accelerated Quantum Computing Research Center is a facility dedicated to shortening the timeline to useful quantum computing. The NVAQC integrates partner quantum hardware with state-of-the-art NVIDIA GB200 NVL72 Grace-Blackwell super chips via a NVIDIA DGX quantum architecture. Researchers and developers can orchestrate these quantum classical systems with the NVIDIA CUDA-Q platform to provide the missing tools to solve processing challenges such as quantum error correction and hybrid application development. The NVAQC is where qubits become large-scale accelerated quantum supercomputers capable of exploring useful applications. Watch the video below and so on. We will not watch the video, but I think there are two interesting components in here. Of course, there are much more, but here we see the kind of chips that are relevant. So there are these NVIDIA GB200 NVL72 chips. In addition to that, there's this DGX quantum architecture and the CUDA-Q, which is the programming language. So CUDA is the one that is being used to program GPUs from NVIDIA to, for example, do machine learning types of work with it. And the Q here is basically adding the quantum functionalities. In addition to that, what is interesting is the target here. So we see on the one side the error correction part, which is something that people are working on in many different facets of quantum computing, because it's a major step towards making these errors which occur in the quantum computer today, which is removing them. So taking a lot of physical qubits as they are in a machine, putting an algorithm on top to abstract them into logical qubits, which then don't have any errors anymore. This plays a very important role in kind of quantum computers, because an error can spread across your whole chip, across the whole system via the concept of entanglement. And therefore, you need to have these kind of algorithms to remove those errors as they occur, because otherwise you kind of create a whole mess on your chip. And these errors, they can always occur. That might just be some space particles hitting your quantum units. So they're very, very fragile, the quantum states. The other thing that is interesting is this hybrid application development. And this targets towards things like, for example, using quantum computers to do machine learning types of tasks. Because here you have, on the one hand, a system that is using the quantum space, so the Hilbert space, with its high dimensions as a variational element. And then on the other side, you need the classical compute element to kind of optimize these variational parameters in this machine learning approach. For example, for a variational quantum solver. And therefore, you need to have both systems, and they need to be able to talk to each other in the learning phase for this optimization. So this is also something that they seem to be targeting here. Now, how NVIDIA changes quantum computing. Many of the challenges standing between today's quantum computers and useful devices can only be addressed with AI supercomputing. The NVIDIA brings these tools to the quantum computing community. So, scaling quantum hardware. Useful quantum computers will likely be data center scale devices requiring integration with conventional AI supercomputers such as the NVIDIA to be controlled and operated at scale. This is something that we've discussed. Then the correcting quantum errors. This is the other one, right? So quantum error correction is a key tool for large-scale useful quantum computers, but its successes rest on challenging computational tasks like decoding. These call for AI and GPU accelerated techniques, which will be developed at NVIDIA. Then there is simulating new QPU devices. So that part we haven't touched yet. So for quantum error correction to work, QPU hardware needs to be highly performant. Rapidly converging on new, more performant qubit designs requires comprehensive and challenging hardware simulations running on AI supercomputers like the NVIDIA. So using simulators to develop new chip layouts with more qubits, for example, that can then scale and later on create a useful quantum computer. And then developing hybrid algorithms, that is the other one we touched already, right? Useful quantum applications are hybrid, requiring both quantum and classical performant hardware. The NVIDIA collocates both hardware modalities, allowing researchers to use NVIDIA QPU to explore truly hybrid applications. And then there's something here on the different components that we have talked about before. So we have the NVIDIA DGX Quantum, the integrated system for quantum accelerated computing. NVIDIA DGX Quantum runs hybrid algorithms, quantum error correction, calibration, and control at max performance. So this is this box here. Then we have the chips we talked about before. So the NVIDIA GB200 NVL2 platform brings the new era of quantum computing to every data center, delivering unparalleled performance for mainstream large language model, LLM inference, vector database search, and data processing through two NVIDIA Blackwell GPUs and two NVIDIA Grace CPUs. And then finally there's the CUDA-Q, which is the programming language, right? So NVIDIA CUDA-Q is the QPU agnostic platform for accelerated quantum supercomputing. The platform's hybrid programming model allows computation on GPU, CPU, and QPU resources in tandem from within a single quantum program and the software needed to run useful large-scale quantum computing applications. And in addition to that, there are some partners that they are working with in the space of quantum technology. Some of them have been featured in a series already. So if you haven't seen those videos yet, again, go check out the playlist about the hidden champions. And then you can also sign up here for additional news to that. Let's quickly hop into the products a little bit more in the detail. So the first one is the NVIDIA CU Quantum, which we haven't talked about yet. So the CU Quantum is an SDK for optimized libraries and tools that accelerate quantum computing emulations at both the circuit and device level by orders of magnitude. So accelerate quantum computing emulations. So this is not actual quantum computing, both for the circuit, so basically the algorithm, as well as the device, so the chip levels. And there we have quick links to Q.Q, and then there are some additional notes here where it's being integrated. So you can run it, for example, on AWS. There's penny lane integration, circuit integration, Qiskit, so the big ones that are known, but also Torch Quantum is, for example, in there, or TCAT, and many others as well that you can see here. The components within this network, within this framework, are this density matrix here, the Pauli propagation, a stabilizer, a state vector, I guess simulator, and a tensor net as well. And I'm not going to go into the details here of all of these for the sake of, one, make this kind of comprehensive, and then two, also to not confuse people and not make it too long. Then there's Q.Q, which I think we have seen before. This is maybe a very interesting thing to know because it shows a little bit how this whole ecosystem looks like. So you have the NVIDIA supercomputing units here, but you also have these quantum backends, and there are many, many different ones. Here's another couple of new ones besides the partners that we saw before. Many of them have been actually featured already here in this Quantum Hidden Champion series. And then the Q.Q basically connects those two physical units together with libraries, programming model, compilers, and tools, and basically delivers the whole framework to orchestrate all of this. Key features are simplifying development of hybrid quantum classical applications, run quantum simulations at scale, simulate quantum systems, write once, run everywhere. So this is the QPU agnostic part, right? Use familiar tools, so Python and C++. And then there's also be part of the community. So they also have a community which is built around this. There are additional information here about, I guess, the speed up that you can get using Q.U, but again, I'm not going to go into the details of this today. Let's quickly check out also the DGX, which is this box which we've seen before, which is more or less like the link between the supercomputing center and the, let's say, quantum computing architecture, as far as I understand. So coupling GPUs and quantum computing. Now superseded the NVU link. NVIDIA DGX Quantum was the first system allowing quantum leaders to integrate the best of quantum and classical processing, accelerate quantum error correction, calibration, and control, and build quantum accelerated supercomputers. NVIDIA DGX Quantum combined NVIDIA Grasshopper superchips and Quantum Machines OPX1000 control system. And Quantum Machines is also a company that we featured before. So NVIDIA announces NVQ Link to launch era of quantum GPU computing. So here we see now the different setups of different kind of implementations. Then I guess this is the link in between, and then here you see the classical supercomputer. It says NVIDIA announces, that one we already had. NVIDIA has developed a high-speed GPU QPU interconnect in collaboration with Brookhaven, Fermi, Lawrence Berkeley, Oak Ridge, Sandia National Laboratories, and other industry leaders. NVQ Link allows the integration of quantum processors with AI supercomputing for tackling challenges like quantum error correction. And then there's a link here to learn more about how that works in detail. The last one is here, this NVIDIA Quantum Cloud. So I guess there's also some way to to work in the cloud with these systems. So what is accelerated quantum supercomputing? I think we've understood this already and not going into the details of this. So here's something about the QDA-QX. Quantum researchers and developers across a wide range of domains, from quantum error correction to hybrid solvers, use GPU programming to accelerate their applications. This demands highly optimized domain-specific libraries. NVIDIA QDA-QX, built on top of NVIDIA QDA-Q, is a collection of libraries and tools for accelerating research and development towards useful accelerated quantum computing. And here you see the industry standard versus the QEC, which is, I guess, part of this QDA-QX. And you see that the error rates are going down compared to, the time in milliseconds is going down at specific physical error rates by a factor of 29 and 35, depending on the physical error rate you're looking at. Here is, I guess, the stack, but we've also seen a little bit about that already before. So you have the quantum resource, the NVIDIA GPUs, system level toolchain. On top of that sits the QDA-Q, and then on top of that you have the hybrid applications, like, for example, in pharma chemistry, weather, finance, logistics, and more. We've seen those different branches of industries that are interesting for that already. Here is some more information about the specifics of it, like Cirq, Qiskit, PennyLane. I think we've also seen that part before. NVIDIA CUPQC, so to ensure the security and authenticity of the world's sensitive data, it is now critically important that organizations migrate to algorithms that can withstand quantum computing attack. The new quantum-safe encryption is known as post-quantum cryptography, PQC. NVIDIA CUPQC provides secure and accelerated implementations of the leading PQC algorithms, advancing data security against quantum computer threats and enabling cryptographic research. This has to do something with the idea of harvest now, decrypt later. I'm not going to explain it in today's video, but again, I refer you to the playlist if you want to learn more about that one. And the NIST-based algorithms that have been proposed to mitigate this. Okay, and then finally there's here this NVIDIA Cloud where you can apply for early access here on the website. And then again, there's some academic partners here that are involved within this, that they are working with together from various different places. You see, for example, here Chicago, Illinois, but also the TU Munich in Germany and other places around the world that are contributing in this. Here's the whole partner ecosystem, which consists out of quantum hardware builders, quantum simulation frameworks, research centers that we've just seen before, and quantum software and systems that are also building on top of that. And then, of course, in the center sits NVIDIA with their solutions. I think that should be it for today's video. I hope that was a good insight for you. If so, please give the video a like. If you have further questions, or if you want me to dive deeper into one of these specifics, then let me know down in the comments below. I'm very much looking forward to that. And as always, stay hydrated and see you in the next one. Bye bye.